All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you have all had an excellent weekend. I hope things have been going okay for you. It was like kind of cold this morning, kind of snowy yesterday, but it looks warm. It looks warm. Tomorrow, I am going to my son's class to take a bunch of microbits. I don't know if you've heard of microbits before. They're like these tiny little single board computers that have a little grid of LEDs on them. And I'm taking them to his class to do some basic programming stuff. And like, I come to this class and I don't really feel super nervous about coming to this class anymore because, I don't know, I've done it a few times. I've been teaching here for a long time. And even though we're talking about really high level stuff, it doesn't really give me a lot of anxiety. But yeah, the prospect of teaching a bunch of grade 4 students about like basic block programming right now in my head, this is a big thing. Like I'm feeling really nervous about all the different things that could possibly go wrong. Um, yeah, with Scratch. So it's like block-based languages, and like I've only got an hour, so I can't really do much. Like we can't spend a huge amount of time thinking about variables and conditional statements and stuff. We're gonna do simple things like, all right, if you shake it, we can make a random number show up, and it's like a dice. Like that's the level of things that we're getting at here. A, a clock that moves, or like a you know what, like a step counter, something like that. That'd be interesting too. Uh, Ultimately, though, I feel anxiety about this. I feel crazy anxiety about this. And so I'll let you know on Wednesday how it went. I'll let you know on Wednesday how it went. Today, what I want you to be able to do by the end of today's lecture is I want you to be able to describe the physical structure of a hard drive. I brought some props today. I have a hard drive here. We'll take a look at the different parts of this hard drive. I'm happy to pass this around after class if you want to see it. It's kind of fun to open up a hard drive just to take a look at the inside and you know, do fun stuff like put fingerprints all over the surfaces in a way that will make this completely unreadable for the rest of eternity. But we'll take a look at some of the parts of this to get a sense of what a physical hard drive's structure looks like. And then once we have that physical structure of a hard drive, I kind of want to move on to, given the physical structure of a hard drive, so we'll take a look at each of these different parts and we'll take a look at how they're connected to each other, and we'll take a look at some abstract concepts related to the physical structure of a drive. Given this layout of a disk, describe approximately what happens as an I/O request for a block or a file is serviced. And I want to think about this in a couple of different ways. The first way that I want to think about this is in terms of scheduling requests for I/O. So we have been talking a lot about scheduling tasks, and now we're going to think about scheduling I/O in terms of being able to decide when we should do an I/O request based on the physical layout of a mechanical disk drive like this. But I also want to think about it in terms of file systems. I want to go back to where we were closer to the beginning of the course and start to think about things like how the physical layout of a drive affects the placement of things like clusters. So we were thinking about this idea of fragmented files in a file system. And when we're imagining all this stuff, we're really imagining it maybe partly because of how I've prescribed it to you, but we're imagining this as this linear line of clusters, this long linear row of clusters. But the reality of the physical structure of a drive gives us a lot more flexibility than just one long line of clusters. And we'll be able to take advantage of this idea once we have an idea of what this physical structure looks like. So we'll take a look at that in a couple of different ways. Before we get to any of that, though, I posted 2 additional sample programs over the weekend. These are the last 2 sample programs that I'm going to be publishing for you for assignment 3. But I wanted to take the time to quickly check them out and kind of see what the expected output from these programs is, so you have a sense of what you should expect to see with your own implementations. So there's two programs that I posted up to this template repository. The first one is NPQ Sketch Tasks. This is a file that will have several different kinds of tasks. The purpose of this is mainly for assessing the multi-level feedback queue to see that this behaves the way that you're expecting it to behave. But it will work with the other policies, and I'll show you approximately what it looks like in terms of output with the other policies. The refiner example is cool, I think. I like it. I think it's cool, but it doesn't really work very well with the multi-level feedback queue because all the tasks take exactly the same amount of time. And so if you do multi-level feedback queue with that refiner example, the observation that you're probably going to make is like, the tasks start and then suddenly they're all done without really seeing any progress in between. And the reason for that is that the display thread, the one that's supposed to be the interactive thing, it actually takes the most time. It takes the most wall clock time to do what it's doing because we put a sleep in the display thread. So it takes the most amount of time to finish. And so its priority gets lowered to the bottom, and then all the other tasks get to run, and they take exactly the same amount of time. And so they'll all move down slightly in the queues that you might have. And so the result is that the output of that doesn't really look exactly compelling when you're using this multi-level feedback queue, because it's not really the kind of workload that the multi-level feedback queue is supposed to be applied to. So this program here has three different kinds of thread types. There are interactive threads, and these are threads that will do just a little bit of work, and then they will return control back to the scheduling policy. There's semi-interactive threads, and these are threads that do a little bit more work before they give back control of the to the scheduling policy. And then there's non-interactive threads. So these are the ones that do the most amount of work. So interactive threads will do a tiny amount of work and then yield. The semi-interactive threads will do a little bit more kind of work and then yield, and the non-interactive threads will do lots of work and then yield. The implementation of this is that what we're doing is the work that we're doing is sleeping. We're sleeping for some amount of time before we give up control after we've printed this thing out. And then the actual part where we're deciding what kind of thread each of these are going to be is that about a third of them are interactive threads, about a third are semi-interactive, and about a third are non-interactive threads. The output here is really just going to be that each of these different threads are going to print out a single character to represent that they've done their work and they're about to go to sleep. And it's to give us a sense of how these threads are being scheduled as the output is coming from them. At the end, we wait for all these threads to finish. We set up our scheduling policy, and then we finish. So I want to go and take a look at this. So this is called NQP thread sketchtasks.c. And what I'm going to do here is I'm going to start by uncommenting the FIFO line here. So FIFO is, I'm calling this init twice. You don't have to worry about supporting calling init twice. I'm just doing this internally for myself to make it a little bit easier for the purpose of demonstrating this. But when I change the scheduling policy to FIFO and I quit this, the NQP sketch tasks will print out all of the tasks at the beginning here. So it's printing out the list of tasks that are in the queue that we're initializing. And then it's running the tasks first in, first out. So the first set of tasks that got put into the queue were interactive tasks. And so all of these are the interactive tasks running through their work, printing the letter I, and then eventually exiting. After that, we submitted the semi-interactive tasks. And so they all go through the process of doing their work, and then they all eventually exit. All of them are printing out the letter N multiple times. So they're not going to be printing this out just once. And then the non-interactive tasks at the end, they all do their work and eventually finish. So in terms of FIFO, this is first in, first out. You should expect the interactive tasks to run first and the non-interactive tasks to run last. If I change this to round robin, and I make this one more time, the output here is that we have all of the interactive tasks submitted first, and then the semi-interactive, and then the non-interactive, and now they're just taking turns. So the interactive task runs, and it gets put to the back of the queue. The next interactive task runs, it gets put back to the back of the queue. The semi-interactive tasks run, they get put to the back of the queue, and they just keep cycling like this. So we have this the same set of inputs that we have for the initial output here, just repeated over and over again because we're just running them in a round robin fashion until they're all done. And then the last part here is going to be where I want to run this as a multi-level feedback queue. So I'm not uncommenting anything because I've got the schedule init set here. These are the settings that I suggested in the assignment document itself. So the queue time allotment is about 1/4 or 1/8 of a second, sorry, and then the boost time is about 2 seconds of wall clock time. When I run this with the multi-level feedback queue, the output here is going to be a little bit different. I'm going to stop this for a second. This is just some additional stuff that I had. This command is now taking standard error and redirecting it to a file. So I was printing some extra stuff out on standard error. You don't need to print that stuff out. This was just for my internal stuff. Here's what I would expect your code to produce, something that looks a little bit like this. I'm going to run this once, and I'm going to run it again. And I want you to observe that there are different outputs here. And every time I run this, I'm going to get different outputs. I'm going to get different outputs every single time I run this. I'm getting different outputs every single time that I run this because if I go back up here to what the threads are actually doing, with the multi-level feedback queue, we're using clock time, actual wall clock time, to measure how much time the task has spent holding the CPU. This statement takes some amount of time. This statement takes significantly more time. Doing a plus plus is a few instructions. This is a load, add, store. Doing write is a system call. And so to satisfy this single line of code, we have to do all of that like mode switch to the operating system. The operating system takes over. It will eventually write to that TTY or that pseudo terminal that we're looking at. It may do a bunch of other stuff, and then eventually we will come back to our code. But how long this line of code takes is completely unpredictable on our part. I can't know how long it's going to take to satisfy a write call. uSleep is a function that we're calling to say, please go to sleep, please suspend me for this many microseconds. But it's really like, please approximately put me to sleep for this many microseconds, because this is also resulting in a mode switch. We're asking the operating system to change the state of our process so that we don't get scheduled for that period of time. In both of those cases, there's a real operating system running under here. There's no control that I have over when my process will get scheduled again. There's another scheduling policy that's working underneath of our scheduling policy. And so the output every time we run this, because we're using actual real clock time, each task is going to run for a different amount of time every time we do this. And so the output here is going to be a little bit different each time, but there are some general observations that you can make about this output. The first is that the very first batch of tasks will be round robin. They all get to go in that first top priority queue. They all get to run once in that first top priority queue. In this run, they all happen to go again in that first top priority queue. Coincidentally, they all got to go again. And so this is that round robin of the top priority queue in action. We see them both taking control at the same, both getting control twice. after that, it starts to look like it's going to be round robin again. But then all these semi-interactive tasks get to take over, and they get to hold that thing for a little bit longer than they were able to before. And then at some point, we're boosting priority throughout this. And then eventually, all of our interactive tasks pretty much finish to completion here. Well, there's still some left over at the bottom here because there's priority boosting that's happening in between all of this and allowing these tasks to come up. But the trend that you see in all of this should be that the interactive tasks get to finish pretty early. There should be very few interactive tasks, if any at all, close to the bottom of the output, and the bottom of the output should be primarily dominated by the non-interactive tasks. These are the ones that will be constantly pushed to the lowest priority queues and allow the other tasks to finish first. You're going to see stuff like there's an interactive task that takes a long time to finish, but again, this is just the side effect of using real actual clock time here and really not being able to predict or control how much time our operating system, the host operating system that we're using, takes to satisfy things like write system calls and how long it takes to return control back to us after we get scheduled off the processor. So that's the first sample code that I wanted to share with you, and I really wanted to make sure that you see the output for MLFQ here and get a sense of it's going to look different every time you run it because we're starting to use like time as a measurement for how much time something actually gets to run on the processor. The other program that I posted is the NQP list insertion code sample here. So this is one of the samples that we did in class that demonstrated race conditions. I'm really strongly recommending that you just use like the textbook sample one, the ++ operation, for showing me that your locks work with p threads. But this is code that's going to test to see if your locks work with our thread structures. This code, I have put a yield right here. And this is the worst case scenario. So if you remember the situation that we had, the race condition here was that if we have one thread of execution that runs this line, and then it's taken off of the processor and another one gets scheduled, we're going to lose the insertion of the second one because it will fully insert its node and then it will be changed to be some other node. With our tasks, with our threads, by putting this yield in here, I've forced it to be the worst possible case. Every thread will try to insert something and every node will get lost. And so in the end, if our locks don't work here or if we don't have locks, the result is going to be that we have 2 nodes in the list regardless of the number of threads that we have. The head node that was there originally, and then the last thread that gets to insert its node. And then a bunch of dangling nodes that are not actually pointed to. So with our lock implementation here, once we add that, these other threads that are going to get control after we call yields, they should just also yield because they're going to get stuck trying to acquire the lock that we're not able to get on this line. So if I run this code, and I'm going to run this code by changing it a little bit. So this is called NQP list insertion .c. I'm going to comment out the lock acquisition here and the lock unlock. And this is the worst possible case. I'm launching 20 threads here, and I'm expecting there to be 21 total nodes. But the worst possible case here is that because we're yielding after that first statement, every node insertion gets lost except for the last one. If I add that back, if I uncomment my lock acquisition, so I make it so that my lock acquisition works, then my expected output here is that I get the 20 total nodes. So I have 20 threads trying to insert something. I should expect to get 21 total nodes in this list at the end. I'm happy to answer any questions if there are any right now, but I plan to have more time for assignment questions on Friday's class, kind of in the same way that we did last week. But I'm very happy to answer any questions if there are any right now. All right, okay, awesome. So those files are up there. If you have cloned this repository, you can pull and you should be able to get those new files, or alternatively, you can just pull them in by downloading them into your directory. I want to kind of step back to this idea of what we did last week with hardware devices and abstraction just very briefly. I want to give some strong emphasis on, despite this Unix idea of single interface being everything is a file, and I think that that's too far, I want to be clear that I still think that that's a really powerful mechanism that we have here. So anything that is able to read and write a file is able to then work with a hardware device without having to know how that hardware device works. In class last week, we took a look at using hex dump with my mouse device. And with my mouse device, again, I have a surprising number of mice attached to this system where I've got a touchpad and a touch screen and a pin interface. And hex dump is a program that really only knows how to read files, but it's able to get data from all of those different interfaces that are attached to my system, all those different hardware devices that are attached to my system, without having to know that they're even mice, without having to know how that hardware works. It just is able to work with that stuff. When we have things that are files, when we have these devices that are files, we also are able to do things like open them as a file and then write to this file descriptor and cause side effects to happen with the devices that we've got. With a mouse, this is kind of a confusing thing, but the results kind of made sense. If I write to this mouse device or something that's similar to this mouse device, I'm able to have the cursor move across the screen. More practically though, writing to files is going to be things like this hard drive shows up as a file in my system. I'm able to write to this drive and cause changes to be made to the actual underlying storage that's on this device. I'm able to write to a file that represents a printer, and the printer will start printing. But I don't have to know that it's a printer. I just have to know how to call the right system call. And so this interface that we have that is being able to read from files and write to files itself is a pretty powerful mechanism to have, to be able to do stuff with hardware without really having to know how that hardware works. But it also means that everybody that writes software has the benefit of, I don't have to know how the hardware works. And all of the hardware vendors or people who are invested in having hardware work, they're the ones that are responsible for writing this code, and they have to write it once for this operating system, as opposed to everybody having to write all of this stuff all over all the time. I think that's a pretty powerful thing to be able to have. Let's take a look at a hard drive. Let's take a look at a physical hard drive. I want to look at a few different things that are related to a physical hard drive in terms of some terminology that I'm going to be using to describe parts of this thing. So I'm going to switch back to OBS here, and I'm going to switch to my big camera. Oh no. I'm going to stop streaming. If you're on the stream right now, I'm going to start it again. So if it stops, please please forgive me. It hasn't made a difference. I'm going to do this. Can't do anything. I cannot do anything. I'm going to quit OBS. Okay. All right, we're back. And I've got a big camera in front of me. So I'm going to view, and then I want to change this to that. No. Oh, boy. That is also not what I want.
Seems like it's working.
I did this once before, and now I'm suddenly lost about how to get back to where I was that time. I think I want to right-click on this, and I want to go to projector. That's what I want to do. full screen projector, and I want this. That's what I want. Okay. Okay, awesome. Yes, there I am. Yeah, okay. So these are this is my physical hard drive right here. You can see that its surface is pretty scratched up already. This drive is no longer readable. This, for the record, it's a Maxtor drive, and it's a 250 gigabyte drive, which is never gonna show up here, despite, yeah, there it is. This is a 250 gigabyte drive. Right there, it's 250 gigabyte drive. So this is quite a small drive in terms of hard drive structures. Now, for now, yes. The first thing that I want us to think about here is the interface. So this is a serial ATA device. In our textbook, the protocol that was described for drives was ATA, and it was really ultimately described as parallel ATA. This is an interface that's called serial ATA as opposed to parallel ATA. The differences between these things is completely irrelevant, and I don't actually care about it. Serial ATA is the more modern type of interface for these things. As long as our main board has connections for a serial ATA device, that's all we really care about, is that I'm able to plug this thing into a main board that has serial ATA connections on the other side. So we've got an interface here. The actual interesting parts are the, sorry, I'll try not to reflect people that happen to be in the hall here. The actual innards of this are what's interesting. The actual innards of this are what's interesting. So what we have here is these things are called platters. This metal device that I'm spinning around now, this is the platter of the drive. This specific drive has 3 platters in it. Each platter here has 2 surfaces. It's got a top surface and it's got a bottom surface. This is not a universal truth with drives. Some drives will have just one surface on them, so the other surface will not be used for storing any kind of data on it. This piece right here, this is the read-write head mechanism. The read-write head mechanism here, and I'm going to come in really, really close. This part right here, that part right there, come on, focus. There. This part right here, this is the read-write head itself. The read-write heads that we have on this, there's one for the top surface. There's one for the bottom surface for each of the platters that we have in this drive. So sandwiched in between each of the platters that we have in this drive, there's going to be 2 read-write heads, and then there's one additional read-write head that's on the bottom of the stack of cylinders that we've got here. So there's potentially, in this case, there's up to 6 read-write heads that can be operating simultaneously. The hardware, this interface that we have here, can really only receive 1 request at a time. But there are 6 separate heads here that can be reading and writing at the same time. So this PCB that's on the bottom, this printed circuit board, sorry, that has these chips on it, surprise, there's a tiny computer inside your computer. There's probably an ARM processor somewhere on here, and the ARM processor has memory that's attached to it, and it's able to do things like caching the reads and writes that are being sent by the operating system. And this entire thing is going to be some kind of an embedded system that will be able to interact with the physical device that we have here. So that's the physical structure of this drive. I'm going to try to go back to this scene. Okay, good. And we are now hopefully back to regular OBS business. That's the physical structure of our drive. There's one word here that I didn't really describe yet, and that word, now I want to go back to my OBS. I'm really sorry. I want to go back to OBS. I'm going to have to quit and start over again. Please forgive me. This is terrible. Here I am nervous about going to a grade 4 class, and I can barely hold it together here. So stream people, again, forgive me. I'm coming back in a second. I want to go to my big camera. I want to go back to window projector, and I want to make this full screen. Yeah, there we go. What I've got here is this structure that I've got. And I'm just drawing on this with a Sharpie. This drive is no longer readable. And I'm going to draw one circle around here. And the way that I'm going to draw this circle is by holding my Sharpie still and spinning the heads if I can. I can't. I'm going to draw a circle around here. I'm going to draw a circle around here. This structure that I've got this is our sector. When I'm using this word sector to describe part of my hard drive, this is approximately what I'm talking about. It's a sector of a circle. So it's like an arc part of a circle structure. Our sectors here are numbered 0, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15. So, I mean, I've drawn 16 sectors on this thing. There are many more than 16 sectors on this drive, but we wouldn't be able to actually see them. And so I've drawn 16 total sectors on this drive. Our operating system and this device have this idea of cylinders on top of this. There's 3 platters in this drive, and every platter and every surface on these platters has the same structure. It has the same sector structure on the top and on the bottom. The numbers are different. They're different sectors. But all of the sectors that happen to be in this inner circle on the same vertical structure here, this is called a cylinder. This is one cylinder of our disk. So imagine taking a slice out of this disk, and I've just taken this part out, and it's going to be a cylinder. It's literally a cylinder shape structure. This is important for us. This is important for us for a couple of reasons. One is that when we start thinking about our file system layout, when we were thinking about it in terms of a linear structure, our idea was that this is the only physical contiguous sector or physical contiguous block to this thing. But the reality is that sector 13 here has, in this case, 6 different contiguous clusters or blocks or sectors. The 6 different contiguous sectors or blocks or clusters are going to be those 6 sectors that are in the cylinder that are physically next to that sector in this drive layout. So if I'm trying to read sector 13 here and my disk is spinning this way, if I'm reading sector 13 right now, the numbered sectors that I have here at 16 at the top and then on every surface beneath it, those are also technically contiguous with this thing in terms of the structure of a hard drive. So when our operating system and when our disk are doing things like scheduling I/O, so they're trying to make decisions about which sector to go to next, they're considering things like this. They're making decisions about which sectors are going to be in the cylinder that are next to the thing that we're currently looking at right now. Our textbook describes a couple of different scheduling policies. I'm going to stop holding it like this because I'm sure everyone's getting super dizzy staring at this thing, and I'm going to switch back to my, my regular scene here. And instead of shaky cam on an actual disk, I'm going to draw these as pictures on our screen here. If we've got this physical structure of our disk that kind of looks like this, and we've got these numbered sectors here that are showing up. So I'll try to write the same number of sectors approximately that I had here before. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I've got fewer sectors in this diagram, but approximately the same idea. If the read-write head that I'm pointing at right now is currently looking at sector 5, it's trying to read this sector right now, and there's going to be another request coming in for another sector, our operating system and our drive are going to have to make a decision about which of the incoming requests to satisfy. So if I have a request for sector 5, that happens to be the one that I'm reading right now, and then I've got more incoming requests. So sector 5 is requested, sector 10 is requested next, and then sector 2 is going to be requested after that. Our operating system is going to have to make, our operating system and our driver are going to have to start to make decisions about which sectors to take a look at here. So sector 10 will require that we move our read-write head to the inner part of to the inner cylinder of this structure that we've got. Moving this read-write head, and now I'm moving it and looking at it, and you're all staring at my screen up here, but I'm moving it. Moving that read and write head takes a certain amount of time, and this is that seek time that they're talking about in the textbook, is moving this thing back and forth. Moving, the platters themselves are spinning underneath this, and moving this read-write head to go to sector 10 here is going to take a certain amount of time. Moving the read-write head back to the outer cylinder to get to sector number 2 after that is going to take a certain amount of time. Depending on the characteristics of the drive, it might be faster for the operating system and for the drive to not move the read-write head at all in this sequence of events here. It might be faster for our operating system and our drive to schedule things such that if this is the currently satisfied request that we're looking at right now, it might make more sense for it to do this first and then this second. In that, keeping the read-write head where it is right now, we'll be able to get to number 2 faster than we would be able to shift that read-write head to get to number 10, even though it's technically right next to the cylinder that we happen to be looking at. This is cool, and this is cool because we can start to think about things like how to actually schedule these different movements of the read-write head in terms of satisfying requests. And there's a couple of different scheduling policies that we considered here in our textbook, and the scheduling policies that we were considering in our textbook, they sure looked a whole lot like task scheduling policies. Really specifically, they looked a lot like the shortest job first scheduling policy. And I'm going to leave this for now. I'm going to ask you this question next time. But when we were scheduling tasks, shortest job first was not a fair policy. Ultimately, I'll come to you in just a second. Shortest job first was not a fair policy. And it was not a fair policy because we got into a situation where we have, one, tasks that could be unfair, possibly. Although in that case, if we have unfair tasks, those tasks are going to take over control and we'll never get to take control back again because we don't have preemption. But it was also unfair because we could have this situation where we've got tasks that are showing up in front of all these other tasks. If we do something that's a little bit like shortest job first with this, and so the description for this was shortest seek time first, so how much time it's going to take to seek our head to that next request. I want you to think about if this is still a fair policy. I'm not going to ask for an answer yet. I'm not going to ask for an answer yet, but I want you to think about if this is still a fair policy when we're thinking about this. And I want you to think about the kinds of properties of the requests that we're making here. So with tasks, it was an unrealistic assumption that we were able to know how long a task was going to take. I leave you with a further question. Is it unrealistic to know how long a read or write request is going to take? I will leave you with that question. Yes?
In terms of the mechanics of how these drives actually work, when you're reading, it's spinning, right? Is it actually reading, is it just continuously reading along that kind of ring, and then it just knows, like, something here, every time it hits the part that's actually trying to read? Or is it sort of mechanic that's like, it's like only reading, like as it's spinning? Like, is it only reading what it needs, or is it reading everything and then getting everything along the ring?
Gosh, okay, so now we're getting into like an electronics question, I think. If I'm understanding your question correctly, I'm not going to try and change my camera here, so I'm just going to hold it close to this and then also gesture wildly at this as opposed to messing things up with the stream again. So all of these read-write heads, as they're moving across the drive like this, they're all measuring magnetism, basically. They're all constantly measuring magnetism. And so they're all sending data to the back end of this drive all the time. And it's this part of the drive's responsibility to interpret that data and then also to begin to do things like correlate the request that was made on your interface for a specific sector into like where the disk is physically located right now in terms of how far it's gone across the cycle of spinning around the disk structure itself. So these heads are just constantly streaming data to this computer system that is sitting on the back of this drive. And this is going to only respond to the requests when they're made. And this also has inside information about the actual magnetic layout of the surfaces of these disks. So it's able to know certain things like where it actually is in terms of where the arms currently are, but then also what sector it happens to be looking at underneath. But that logic is on this part of the drive as opposed to being encoded necessarily on this part of the drive. I don't know if that answers your question. I hope it does. But I kind of have to lean toward, if you're interested in this, take a computer engineering course that's on electronics and stuff, because I might just be making this shit up. I'm a CS person and not really a computer engineering person. What I've learned about this, I've learned from YouTube. Yeah.
If I'm not mistaken, it's just a really complicated like record player, like the hard drive.
Yeah, I mean, I guess yes, except if the read-write heads were to actually touch the surface of the disk, they would destroy it.
That's true.
Yes, and I mean, record players are destroying the records just a tiny bit every time you play it, but these would irrevocably destroy the surface of the disk if they touched it. You would not be able to recover from that.
That's what I mean by complicated.
Yes, it's a very complicated and also extremely fast record player. This disk, I don't know if it says on here, but this is probably a 7,200 RPM drive. There are physical disk drives that go in data centers that can spin up to 15,000 times per minute, which is intense. Yeah.
And record players are like 36 RPM.
Yeah, exactly. So it's quite a significant difference between the two. So the other part that I want to think about this is, when we were thinking about our file system here with exFAT, and when we were thinking about this idea of fragmented files, so when I gave you these sample volumes for the exFAT volumes, one of them was called fragmented.image. And the way that I made this image was by filling it with a bunch of tiny text files. So I started initially by putting all these text files into the file system. And what that meant was that text file number 1 would show up in cluster 4, text file number 2 would be in cluster 5, text file number 3 would be in cluster 6, text file number 4 would be in cluster 7. And then I went through and I deleted half of them. So now we still have text file number 1 in cluster 4, but there's nothing in cluster 5. But there's text file number 3 in cluster 6 and nothing in cluster 7. And text file number 5 in cluster 8. But all the ones that were in the middle were unused. And then I took a big file and I said, there's enough space for this big file, so use up all these remaining clusters. And that resulted in this fragmented file system in terms of us thinking about this structure in a linear way. But once we start to change this structure and we begin to put it in a circle, and we put these circles on top of each other as cylinders, suddenly we've got a situation where, hypothetically, sector 2 here, cluster 2, block 2, I'm using these all interchangeably right now just for the sake of discussion. This is technically contiguous with whatever cluster, sector, block this is, even though it's on another surface of the disk. And it might even be on a completely separate platter on the disk. And our file system, when it's choosing to put these things in contiguous locations, can begin to make decisions like this. Our operating system, when it does come up, knows more about the disk's physical structure than we do. So when we were working with volumes, we were working with files. But in terms of the actual geometry of this drive, our operating system knows everything about the geometry of this drive. It knows about how many platters and surfaces and stuff there are. It knows about how many sectors there are. So it's able to do logical requests for sectors and logical placement of sectors in appropriate locations. All right, okay, so at this point, you should be able to describe the physical structure of a hard drive. So the terminology that I'm looking for you to use here are platters, surfaces, sectors, read-write heads, interface, cylinders. Those are the main things that I'm looking for you to be able to describe. Yeah?
So the surfaces, it's like each side of the platter, right?
Each side of the platter is a surface, yeah.
With ones that only use one-sided, does that still have two surfaces, or is it just one?
It would be one surface. So if the disk only has like a top read-write head, then it only has one surface per platter. Yes, physically there are two surfaces to this thing, but in terms of abstractly, there's one surface to this thing. I also want you to be able to, in a very hand-wavy way, describe things like, given a disk layout, describe what happens as an I/O request for a block or an I/O request is being serviced. We're going to think a little bit more about these I/O scheduling policies next class, and then we'll start to move into virtual memory after that. That's it for today. If you're watching this stream right now or after the fact, I apologize for the flaky back and forth. Otherwise, everyone here I think was happy with that. I think. I mean, it was a giant mess, but yeah. I'm thinking about like going to grade 4 class right now. Sorry. I'll let you know how that goes on Wednesday. I hope that you all have a great rest of your day, and I'll see